of this paper, Space-Time Algebra as a Powerful Tool for Electromagnetism. And we are very slowly creeping through this work. And where are we now? Well, we are at bivectors product with bivectors. We're going to finish up that section very quickly. There's not much left there. And we're going to get through complex conjugation. And then we end up in this very important section about relative frames and paravectors. And I think before we dive into that, we are going to study three-dimensional geometric algebra. And that may take a lecture to cover at the level we need to sort of warm ourselves up to this. Notice this paper doesn't teach three-dimensional geometric algebra. However, what we learn about is that these paravectors, these notion of paravectors, that essentially is regular 3D Euclidean geometric algebra, 3D EGA, right? And so I thought we'd spend a lecture or two just studying 3D EGA so we can appreciate what paravectors are. But that's not for today. That'll be for starting the next lecture. So right now, let's just finish up bivectors and complex conjugation. So let's begin. So we stopped last time showing that our bivector spacetime product, we obviously know about the general spacetime product of two bivectors will have at most these three different blades, and we discussed the circumstances where f and g are, where little f and little g, these canonical components, can be used to express this symmetric sum of this product, which will be the complex scalar part of the spacetime product, so it's just these two pieces, and how the bivector part is given by this antisymmetric part. So that's fun. And then they give us a little bit, in fact, it'll become clear after we introduce relative three vectors that this real scalar is completely equivalent to the usual Euclidean dot product from non-relativistic three-vector analysis, which motivates this choice of notation. So what they're going to show is that eventually we're going to find this three-dimensional algebra I was just alluding to earlier inside our geometric algebra. And we're going to discover that this dot product, this bivector dot product, actually mimics regular Euclidean dot products from your classic three-dimensional Gibbs Heaviside mathematics, right? The old x hat, y hat, z hat. I can do a better hat than that. I can do a better z and a better hat than that. Z hat, I, j, k, right? Those unit vectors, the classic stuff. It's all built inside this, and we're going to see that next time. But what's interesting is that it's this bivector dot product that's going to end up helping us do stuff like x dot y, which is 0 in the Euclidean system, the Cartesian Euclidean system. But this dot product here in that 3D system is actually related to this bivector dot product. That's the symmetric part of this. So that's going to be really interesting to see how that works. So moving on, it follows that the total dot product between arbitrary bivectors will have scalar and pseudoscalar parts of this form. So that comes directly from this, right? This expression here, that exponential part is clearly cosine theta plus phi plus sine theta plus phi times the pseudoscalar basis vector, right? That's a literal substitution, right? And it's clear that since this is a real number, right, because those are two time-like bivectors, and it's the symmetric sum. And we kind of worked through some exercises yesterday, or the last lecture we did. We worked through some exercises convincing ourselves, if not proving it, that this will always be a real scalar. So that's a real scalar. So this is a real scalar. So that's clearly got to be, so this part here clearly has to be that, which is literally what is written here. And this part here obviously has to be that. That's literally the same thing. So with that in mind, that's not too hard to understand. And then they say, note the intrinsic phases of f and g play a critical role in these products and produce wave-like interference factors. it is worth emphasizing these factors arise solely from the structure of spacetime itself and not from any additional assumptions. So, all right, so really, here's what, when I look at this, perhaps naively, what I say is, okay, the scalar part oscillates depending on the exact canonical expansion of f and g, right? That canonical expansion is going to give you this phase factor, and both of these phase factors, right? And so the partitioning of the space-time product of f and g into its grade 0 part and its grade 4 part, that partitioning is definitely going to depend on these phases. I guess I want to quibble with this word interference. And the reason I want to quibble with it is when I think of interference, I think of a single quantity, say Q, and that quantity is dependent on a bunch of stuff. And inside that bunch of stuff, and usually that bunch of stuff is somehow made positive definite, and usually that bunch of stuff inside, there's a trigonometric term somehow buried inside this bunch of stuff. And that trigonometric term depends on a couple different factors. So it would be, for example, Q would depend on, say, psi and phi, and then Q ultimately equals something like psi squared plus, it'll be something like psi plus phi quantity squared, right? And inside here, when you blow this up, you end up with some kind of term, that psi phi perhaps, that allows, that has a sign change as these things depend on time. Usually, psi is time dependent and phi is time dependent. And therefore, this guy actually depends on the interference between psi and phi. And that's manifested usually in something like this. That's your classic sort of physics way of doing it, right? This is different, right? This is two different quantities that are, in some sense, conserved in their totality, and that partitioning is split. Now, if there was a single quantity that depended on both of these guys, then that quantity, sure, would, especially if it was dependent on the product of these two, that would be something I would call interference. So I guess what I'm saying is I'm not happy to call this interference. For example, you could think of it this way, right? You could think of it as, imagine just have a vector in regular space, right? Your classic vector, and it has some angle. And the projection in the x, say this is v, well, we call that vx. Well, that's vx is equal to v cosine phi. And vy, right, vy equals v sine phi. Well, you don't say that vx and vy, so this is vx, right? This equals vx. You don't ever say that as phi changes, and this thing sort of goes around in this circle, we never say that vx and vy exhibit interference, right? We just say that the projection depends on an angular variable, right? So likewise, I kind of feel like the same thing is happening here. So I'm not so sure about the profundity of this. However, they like to point out these factorize solely from the structure of space-time itself. Well, I guess that's pretty clear from how we develop these angles. In other words, those angles don't literally exist in space, right? They came to us from the structure of the geometric structure of f and g through this canonical expansion, which was somewhat abstract. So I do appreciate that. I'm a little concerned about the notion of interference for this particular term. It doesn't jive with my physical intuition of, well, my physical expectation of what interference is. However, we're just one application away from convincing the otherwise, and as we read this paper, I'm sure we may get to that place. Okay, moving on. I think we've gone through this part plenty of times, right? We've shown that the definition of this commutator bracket, you'll only get a blade 2 object, so that's easy. We'll explore the deep significance of this commutator bracket, where it will play the role of a Lie bracket for the Lorentz group. Yeah, I'm pretty excited to get to that stuff. Motivating the choice of notation. And for completeness here, we also define the bivector cross product as the Hodge dual of the commutator bracket. So it's really hard to appreciate this early in the paper why this is important, but it becomes important when we talk about paravectors later on. But what is key here is that this ultimately is going to be exactly equal to a regular cross product from Gibbs Heaviside three-dimensional regular vector analysis. This is going to play an important role. I will note that if you check out other papers, this is sometimes written in a little bit more direct way. Well, a little bit, I guess, I don't know, more direct, less direct. But it's written as FGI, where I like it this way better because this is just the dual of the blade 2 part of the space-time product of F and G, right? And then you just flip the sign. Remember, since I equals -1, it's pretty clear that I inverse equals minus I, right? And that's where I'm getting that -1 from. So I'm getting rid of that inverse and I'm putting that minus sign there. That's actually pretty typical from other papers that I've seen. Okay, so after we introduce the relative 3 vectors, it will become clear that this cross product is completely equivalent to the traditional 3-vector cross product. Again, motivating the choice of notation. So this idea of these 3 vectors and traditional 3 vectors being buried in this, that's really, really important to the study of space-time algebra. And what they're trying to do is, instead of demonstrating the existence of this the traditional 3-dimensional vector algebra inside as a subalgebra of space-time algebra, they're introducing the machinery of space-time algebra, and then they're going to show you how that machinery applies, which is completely fine. Like I said, the traditional ways you would know 3-dimensional geometric algebra before learning space-time algebra. But this paper is saying, no, you don't really have to. We can just start with the rules of space-time algebra and then discover all the rest of it, which is kind of fun too. Okay, so let's move on to the next section. All right, complex conjugation. So somehow we are going to take the analogy of a complex number that we are all familiar with, where z, a complex number z, is a plus ib, and we know that this becomes a minus sign in regular complex conjugation. So clearly something like that is going to happen in our algebra. Now in our algebra, the complex quantities we deal with are complex scalars, alpha plus beta I, where alpha and beta are real, and complex vectors, v plus wi, where v and w are vectors. So beta I, right, this is the pseudoscalar, and this is the pseudovector. This is a grade 4 object, and this is a grade 3 object. So now we're going to start generalizing this notion of complex conjugations to those circumstances. Now take note, there is something that is important to understand here, that there's a couple different things in our geometric algebra whose square is -1. Right? We definitely know that gamma 0, 1, 2, 3, that this guy's squared is -1. But also take note that, say, gamma 0, 1, right? If you take gamma 0, 1 times gamma 0, 1, this guy is going to square to, well, you see, you'll pick up a minus sign, you'll get gamma 1, 0, 0, 1. Then you associate the zeros and you square the 1 and you end up with +1. So here's something that squares to positive 1 that's not 1. Gamma 0, 1 is a bivector, but it squares to positive 1. However, had we done what I intended to do, which is gamma, say, 1, 2 times gamma 1, 2, you flip the 1 and the 2 to get gamma 1, 2, 2, 1. You get a minus sign for the flip, and then you do the associations, and you get a total of 3 minus signs, so this equals minus 1. So gamma 1, 2 space-time squared equals minus 1. So here's another object whose square is minus 1 that's besides the pseudoscalar. And it turns out that all of the purely space-like basis vectors have this property, and all of the purely time-like basis vectors have this property. And those are all important. But so when we talk about complex conjugation, if we just say, take the thing that squares to minus 1 and change its sign, we better be a little careful because there's a couple things that square to minus 1. It does turn out that the one we're interested in this section is just the pseudoscalar. But just take note that there's more than one thing in this algebra that squares to minus 1, and that will be very important. Okay, so let's begin reading. At this point, we define another useful operation, complex conjugation. I'll just take this opportunity to point out that the one operation that really matters is space-time product, right? Space-time product, everything is an addition and vector addition. Those two things are built into the algebra. Everything else is a variant that is convenient for us to introduce, but is not necessarily fundamental to the algebra. So let's keep in mind, these are the two fundamental things, and everything else is just something we do. I don't want to say it's just bookkeeping, but it certainly feels that way sometimes. Okay, so the proper inverse of a bivector has the canonical form F inverse. So they give this presentation as the canonical form of the proper inverse of a bivector. So remember, the canonical form of any bivector has got to be G times X phi I, right? So this has that form, right? This is a bivector here, and this is an exponential. So that does count as canonical form, even though it isn't literally in this form with a positive exponent. But it is a bivector times a phase factor, if you will. So they cite 3.28 and 3.18 to develop this inverse. So let's run that down. So this is 3.18. It says that you have any multivector, its inverse is literally defined as its reversion divided by its reversion squared. And 3.28, of course, says that the canonical form of a bivector f, this is now a bivector f, is some other bivector times this phase factor. You can always put it into that canonical form. So we're going to combine these two together. All right, so by definition of 318, the inverse of this bivector, because a bivector is a multivector, is the reversion divided by the reversion squared. Okay, so the reversion of this form, right, that reversion is going to be, we execute it recursively. We reverse these two parts, and then we execute the reversion on each part. So I get e to the phi I reversion, f reversion. Now, what's really fun is that I reversion is equal to I. You should figure that out. Make sure you're comfortable with the fact that I reversion is equal to I. F times F reversion, I've just written that right down here. Again, I reversion is equal to I. So these two guys combine, and they're in the denominator. So I bring them up here, so I get minus 2 phi I. This is just e to the phi I, getting rid of the reversions on the pseudoscalar basis vector. Then we're left with f reversion over f times f reversion. So that's this part right here. So these two combine nicely and give you e to the minus phi I. F reversion is minus the magnitude of f squared. We've demonstrated that a few times, I think. And then you're left with f reversion on the top, but you've got this minus sign on the bottom. And what the thing that you have to sort of know or recognize is that the reversion, this is a bivector. F is a bivector. So the opposite, the bivector times -1 is its reversion, right? When F is, when 4, this should be 4, for F, a bivector, right? So imagine that here's F, right? Well, if you put a minus sign in front of everything, right, and you change all of these to minus signs, well, what have you done? Well, you can do that a different way, right? You can do that by just switching all of these around. 0, 2, 0, 3, 2, 1, 3, 1, 3, 2. So F reversion equals minus F, right? So with using that fact, we get rid of this minus sign and that reversion, and we're left with this. And this form here is exactly what the paper is advertising, right? So this isn't totally straightforward. You do have to take note, in order to get to this spot, you do have to take note that F reversion is minus F, right? That is an important little fact to get there. Now, given this definition that we just verified, can we demonstrate that it is, in fact, the inverse? Let's exercise that. So we have F, its canonical form is F e to the phi I, and this is the canonical form of F inverse, so we just multiply the two together, right? So we get F e to the minus phi I over magnitude of F squared, F e to the phi I. Now, bivectors all commute with the pseudoscalar, right? So I can just move that pseudoscalar in there, and these two exponential terms, they cancel right away. So I end up with F squared over the magnitude of F squared. Now, right away, you should know that these two have the same magnitude, and this cancels to 1. But if you wanted to dive in a little bit deeper and go through our definition of F from Hestenes's paper, you can replace F with rho to the 1/2, this canonical vector R times I. You may remember that from Hestenes's paper. But if you do this and you replace F squared with two products of F's definition, you end up with the two i's come together because they commute, because R is a bivector. And the two i's come together to give you this negative sign. The two rows come together to give you this, the two rows come together to give you the row. The two i's come together to give you the negative sign. And then the two r's come together. And each R is literally defined as F times F reversion to the minus 1/2, right? So if I replace the two R's with F reversion to the minus 1/2, you end up with two F's on top, F reversion on the bottom, right? And let's see, what's the next step? I think the next step is, I think I had it wrong before, but now I'll just take that minus sign and put it here in front of the F. Let me do that in green. I'll take this minus sign and put it here, right? So that goes away. And then this becomes, and I'll get rid of that, and I'll make it F reversion F, right? So these two cancel. That minus sign is gone, and rho and F squared, those are the same by definition. So this guy equals 1. All right, good. So we've demonstrated that the paper is not lying. So we've kind of examined and demonstrated this point. To more compactly write this inverse, so I guess they're interested in attacking this canonical form. We introduce a complex conjugation of the spacetime algebra as a flip in the sign of the pseudoscalar. So that answers our question about multiple things that square to minus 1. Forget those other things. We're only interested in gamma 0, 1, 2, 3. That's the pseudoscalar. Notice they call it the pseudoscalar. I'm going to start using that language too. This is the pseudoscalar. There's a pseudoscalar would be beta I. That's a pseudoscalar. But the pseudoscalar is just I, all right? So I like that language. and we introduce complex as a flip in the sign of the pseudoscalar. For any multivector M, as in 3.23, this produces, and they're going to create this new notation. So given a multivector M, its complex conjugate is M with the little star, right? That's opposed to any of these other forms that we might be interested in, right? We might want to go with M bar, for example, very common, but they're going to go with M star in this paper. And they say M star is M where I is replaced with minus I. So when they're referring to 3.23, although I'm sure they're referring to alpha plus vector plus, I guess, canonical form of bivector, right, plus trivector, which I think they used as a fractor, plus pseudoscalar, right? That was what M equals. Let me write that a little cleaner. So you have the scalar part, the pseudoscalar part, the vector part, the dual of a vector, which is the trivector part, and then this bivector part we're writing in canonical form. So if we take its complex conjugate, we're switching the signs of all of the i's we see, right? So the canonical form, the phase changes, but F is left alone, which is really important, right? F is left alone, but the phase of its canonical of F changes. And then we flip the sign of these two pieces right here. And those two sign flips are manifest here and here. And notice that they've combined it. So this piece, they're already looking at this as though this is the real scalar. This is the this is the complex scalar. This is the complex vector. And they've just changed the sign in the complex scalar or complex vector. Normally, this would have been a plus and a plus, right? If I take M and I combine into a complex scalar part, I would have taken this, merged it with A. I would have taken this, merged it with V, and there would have been plus signs there, right? But we're taking the complex conjugate of it, so we switch those to minus signs. This one too. Okay, not hard. So geometrically, the flip in the pseudoscalar sign corresponds to changing the orientation, the handedness of spacetime. Since the conjugation of a conjugation is M, it's an involution on the algebra. It's an involution. Okay, I think that's pretty straightforward. If you flip the sign twice, you come back to where you were for this kind of thing. All right, for complex vectors, the conjugation is equal to the reversion. Okay, of note, conjugation is equal to reversion for complex vectors. So, given a complex vector z, we notice that v plus wi reversion equals v plus iw, right? That's what reversion is, but which is v minus wi, right? So the reversion is literally just switching w and I, but that equals v minus iw because the pseudoscalar anti-commutes with all vectors, right? That's the important thing to remember is wi always equals minus iw, right? There's anti-commutation. It commutes with bivectors, but it anti-commutes. It anti-commutes with vectors. So because of that, z reversion equals z conjugate when z is a vector. When z is a complex vector. When z is a complex vector. It's not too difficult to see. However, this anti-commutation also forces us to be careful about applying conjugation to products, since it does not distribute across products that involve vectors. So we have z m, where I presume m is an arbitrary multivector, right? So the conjugation of the spacetime product of z and m does not equal m star z star, which is what you'd expect. You'd expect this sort of recursive conjugation because z m star does not equal z star m star. So that's worth looking at. I don't like the word. The thing that confused me there is this word distribute. What we just observed was not really distribution, or at least not at this level of appearances. Let's quickly have a look at that. So I guess we just test this out with a complex vector v plus omega I. This is a complex vector. And this is just some multivector. This is like, I picked an even one, alpha plus a bivector f. So f is meant to be a bivector here. So you have a vector, a trivector, a bivector, and a scalar. And by multiplying the two together, I get this expression. And then when you take the complex conjugate, you change the sign of just these two parts. You get this minus sign here and this minus sign here. However, if you calculate what you would expect in the normal rules of complex conjugation, you end up with, instead of VF, you end up with FV, and those do not commute. So these two here are definitely different right away. And then you have, this is also different from this, right? And F and V don't commute. And you could commute the I and the W, and then you would get a positive sign, but that would be wrong too. So clearly, you've got to be, so this is just a demonstration that this doesn't work in general for multivectors. However, you can see that if we treated this as a complex scalar, right, and V and W were scalars now, pretend that they're scalars, and this is some kind of multivector that's just even multivector, well, now this does commute, right? So this would commute and you would get VF, and if omega was a scalar, you would get minus omega Fi, right? In other words, I'll get rid of all those green things I put in there, right? If we changed our convention and V and W were scalars, then this guy would commute to that, and then this guy would commute to that. So complex scalars are fine. It's these complex vectors that kill your nice rule. So that rule does not apply in general. And I guess it shouldn't apply in general. I mean, it's not a fundamental operation in the algebra, right? It's sort of a convenient bookkeeping thing. It just doesn't work perfectly. Okay, so moving on. To aid memory about some of these subtler properties, we have collected a few commonly encountered identities in Table 5. All right, so we'll look at Table 5 in a moment, but, well, let's look at Table 5 right now. So here's Table 5. Table 5. What do we got? We got, I don't see any conjugations here. I don't see any conjugations here. But we do see bivector pseudoscalar commutation. So bivectors and pseudoscalars commute. So in here, zeta is a pseudoscalar. So those commute. And bivectors pseudoscalar complex conjugation does work as expected, right? Which is what we well, if this is a pseudoscalar, yeah, that's obvious, right? So, well, we just did it. Vector pseudoscalar anti-commutation. So here we have, let's see, so we have, that's the anti-commutation of a vector and a pseudoscalar. So that just shows you this equality is true. It's a weird way of showing it. I suppose you could just have written omega I equals minus I omega, right? That's sort of the same thing. But I think they're doing it this way because they want to get into Z conjugate equals Z reversion when you're talking about a complex vector, a complex vector's conjugate is equal to its reversion. But you lose this sort of recursive conjugation property. All right, are there any others in here? There's this one later on here. Here's complex conjugation, but it's in something called relative reversion, which we're not ready to talk about yet. So yeah, there's table 5. Very nice. And now we just point out with this operation, meaning the complex conjugation operation, we can write the complex generalization of the blade inverse. So the inverse of the complex scalar is the conjugate of the complex scalar over the conjugate times the complex scalar itself. So that deserves a quick test. Well, this one's really easy to see, right? If you have a complex scalar, alpha plus pseudoscalar part beta I, its complex conjugate is minus beta I, and, well, just like complex numbers, right? The denominator, conjugate times the original complex number, that's going to give you alpha squared plus beta squared, with this plus sign here comes from the fact that this you pick up this minus sign from the product and then another minus sign from I squared. And then you end up with alpha minus beta I at the top. And it's pretty obvious that if you multiply this times alpha plus beta I, which is zeta itself, this is all going to end up equaling 1. So that's pretty clear. This second one here is kind of interesting. This is a complex vector inverse, right? So you have a complex vector. What is the inverse of a complex vector? And you get this expression. This is actually pretty interesting. So let's flush this one out. So the first thing to take note about this, I think, is the fact that we're using basically a bit of a recursive, almost recursive definition for the inverse of a complex vector, because a complex vector's conjugate multiplied, space-time multiplied by itself, that is a complex scalar. So this part here is going to be a complex scalar. And we've just learned the formula for calculating the inverse of a complex scalar. So we're going to actually use that formula in our formula for the inverse of a complex vector. So if we take our complex vector to be v plus wi, where v is a regular vector, w is a regular vector, but we're taking the dual of w, which turns it into a pseudo vector, which we really have to understand is a trivector, right? It's a trivector. So, and its complex conjugate under our definition of switching the sign of I is very straightforward. So now let's calculate z star z, which is pretty easy to calculate when you blow it all up, remembering that vectors and the pseudoscalar anti-commute, right? So when I move this I over to the right of v, I pick up a minus sign, and that minus becomes a plus. Likewise here, when I move this I past the w, I pick up a minus sign, and then the two i's come together and form another minus sign, which cancels out. So that leaves this minus sign behind. So you end up with v squared minus w squared plus vw And that's what zz conjugate is. So now I need the inverse of zz conjugate. So zz conjugate's inverse, we use the formula we just learned before, right? This one here, right? This formula for the inverse of a complex scalar. Well, first take note, this is a complex scalar, right? You have a scalar part, and vw plus wv, right? That's the symmetric sum of the space-time product of v and w. So we know by definition that that symmetric sum is the grade 0 part, which is scalar. So you got to keep this in mind, right? You've got to remember these symmetric sums and how these things are defined. If this was the anti-symmetric sum, this would be a bivector. But it's not, it's the symmetric sum. So this is a scalar. So a scalar times the pseudoscalar makes for a grade 4 object. So so this guy is a scalar plus a grade 4 object, which is a scalar plus a pseudoscalar. So this whole thing is a complex scalar. Ergo, we use this definition, and the numerator is the complex conjugate of z star z. So whatever this was, you take its complex conjugate and you throw it in the numerator. So that only changes this sign from a plus to a minus, right? And then the denominator is the z star z's complex conjugate times z star z. So this is z star z, and its complex conjugate, of course, changes this to a minus sign, and then times z star z. And then that's sort of, we know from our complex analysis that such a product is just going to be the sum of the squares of these components here. So we get v minus w omega, v minus w, v squared minus w squared squared. Remember, v squared and w squared, by the way, are also obviously scalars, right? Because any vector space-time product with itself is a scalar, and that's part of the structure of the algebra. So we've gotten to this part. We've gotten as far as this, this inverse, and that inverse looks like this. The rest of the definition is to take that inverse and multiply it by z conjugate. And then we have z inverse is this thing here multiplied by the conjugate of z. And then there you have it. And then you can just test this out pretty quick by just multiplying z inverse times z, better give you 1. Well, then z is v plus omega I. This guy here ends up being v squared minus w squared plus this symmetric sum times I, and here you have the minus, and of course that's going to actually add up to be exactly this, and you're going to get 1. Very nice. And that just leaves this one over here. This one is actually pretty simple. It's much easier than this one was, so we'll leave that one for you to do yourself. And here they use some of these identities which we used before. And then our next topic is relative frames and paravectors. So this is a very, 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 very important topic. And like I said, we're going to take a break and we're going to study the 3D geometric algebra for a lesson or two, just to prepare ourselves to really appreciate the significance of this notion of relative frames and paravectors. It's a very important organizational concept in the space-time algebra, and it's worth approaching with great focus. So with that, I'll see you next time.